Students tell me all the time the malonic ester synthesis looks like a monster. Several steps, so many arrows. But the truth is, you already know every single step in this mechanism. All we're doing is chaining together things we've seen before. Enolate alkylation, hydrolysis, decarboxylation, and tautomerization. Let me show you how simple this pattern actually is. Hey there, ninjas. Today, we're turning a big, intimidating name, the malonic ester synthesis, into something you can actually use on an exam. This reaction often appears at the very end of the carbonyl unit, and that's because it's a capstone reaction. It ties together a lot of things you've already learned. Carbonyl alpha proton acidity, enolate chemistry, nucleophilic substitution, ester hydrolysis, decarboxylation, and a tautomerization at the end to pull it all together. By the end, you'll know more than just how it works. You'll know how to trace which carbons in the product came from the original starting material and which came from your alkyl halides. When chemists say malonic ester, we almost always are referring to diethylmalonate. These ester groups are almost always ethyl esters. They could be other things, methyl isopropyl. That's not the important part. The important feature is the alpha proton sandwiched between the two carbonyls. That makes it unusually acidic, easy to deprotonate, and easy to turn into a stabilized enolate. Alkanes have a pKa around 50. Traditional alpha protons have a pKa around 20 to 25 or so. Being sandwiched between the two carbonyls gives this proton a pKa of around 10, much more acidic than we would otherwise expect. Once you make the enolate, you can alkylate it once or even twice. After that, you hydrolyze the esters, lose carbon dioxide in a decarboxylation, and a final tautomerization gives us our final product, a substituted acetic acid. We start the first part of the malonic ester synthesis with a base whose identity matches the identity of the ester, ethoxide for ethyl esters. We use our base to deprotonate that especially acidic alpha proton, creating a stabilized enolate. The enolate is so stable because it is resonance stabilized by both of the original carbonyls. That means in the first step, it doesn't matter which direction you push the electrons up into. They're all related through resonance. Now the enolate will do what enolates love to do, act as nucleophiles in an SN2 enolate alkylation. This works best with methyl primary alkyl halides, maybe benzylic or allylic. I'm using the bouncing arrow notation here to show that it's the central alpha carbon that acts as the nucleophile to attack the alkyl halide. If your instructor isn't using bouncing arrow notations, they probably should be. I have a video that I'll link to down below that explains how bouncing arrows are a game changer when it comes to drawing mechanisms. Watch that video, then send it to your instructor. See if you can convince them to switch to bouncing arrows. Be sure to number your carbons for this step. When students make a mistake in this step, it's often because they drop a carbon when connecting carbon 2 to carbon 4. Carbon 2 doesn't become carbon 4, there's a new bond formed between carbon 2 and carbon 4. If you add only one equivalent of base and one equivalent of alkyl halide, you'll add one alkyl group to your malonic ester. If you repeat the sequence, base again, then a different alkyl halide, you can build in two different substituents. After alkylation, we hydrolyze both of the esters under standard hydrolysis conditions. Adding aqueous acid turns both esters into carboxylic acids. The result is a malonic acid derivative, basically malonic acid with two alkyl groups attached to the central carbon. And if we had stopped at standard hydrolysis conditions, our synthesis would stop here. But there's an important additive in our step 3, and that is the presence of heat. Heat allows us to do things we wouldn't otherwise normally be able to do. Heat allows us to get over higher activation energy barriers than we're used to. When you heat a malonic acid derivative, one of the carboxylic acids leaves as carbon dioxide. A 6-membered cyclic transition state expels carbon dioxide and leaves us very close to our final product. The decarboxylated product has an enol embedded in it, and under acidic conditions, that enol will tautomerize back to the carboxylic acid. Once you see the pattern, enolate alkylation, hydrolysis, decarboxylation, and final tautomerization, the malonic ester feels less chaotic and more predictable. Now, here's the key ninja-level exam skill. The alpha carbon of the final substituted acetic acid is the original alpha carbon of our malonic ester. Any substituents on that alpha carbon came from the alkyl halides during the SN2 steps. One of the carbonyls is lost as carbon dioxide. The other carbonyl survives as our carboxylic acid. If you ever find yourself forgetting, always ask yourself, what survived decarboxylation what got added during alkylation. During lecture, the malonic ester synthesis is often taught at the same time as acetoacetic ester synthesis. I have a separate video that I'll link to down below that'll walk you through the acetoacetic ester synthesis. But ninjas, the pattern is identical. Stabilized enolate, alkylation, maybe a second time, hydrolysis, decarboxylation, tautomerization to the final product. The only difference between these two reactions, one is an ester, one is a ketone. The malonic ester starts with an ester and ends with a carboxylic acid after hydrolysis. The acetoacetic ester starts with a ketone and ends with a ketone in the final product. Now you've peeked back behind the curtain and seen what's really going on. A sequence of steps you already know strung together to form a very sophisticated looking product. If you want to cement this pattern even further, your next stop should be the acetoacetic ester video. It's the perfect comparison. Take a breath. You've earned it. On to the next one, ninjas.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.